All right, so this is libsigmf. This is a C++ library for dealing with SIGMF data sets, and I'll talk a little bit about that more in the future. I'm Nathan West. I've done quite a bit of development for GNU Radio and Volk in the past, and now libsigmf is available on GitHub. More details later. So this is in partnership with the UC Berkeley. So they're going to be releasing some data as well. I'm going to be presenting some information from them. I am not really an astronomer. I'll do my best to present their information, but I'm really just going to point to their resources, and you can go online and contact them if you're interested in the details of that kind of stuff. I'll be sure to point out where it is. So what is SIGMF? It's the signal metadata format. I guess there was a GNU Radio Hackfest last year or 2 years ago here at FOSDEM, right before FOSDEM, where they came up with do this. So the actual specification is licensed with Creative Commons, so you can basically use it for whatever you want, just give attribution. And the general idea is that you have two files. One is this SIGMF data file, and one is this SIGMF meta file. The meta file is just JSON, and the whole structure of SIGMF is really just not around exactly how to store stuff so much, but it's more about what keys and metadata do you use to describe your signals that you've recorded. And then the SIGMF data is really, you specify what the format is inside the meta file, but in general, it's just samples written to files as plain C types. So the goal is really just to keep metadata consistent, because everyone uses different ways of capturing their sample rates and center frequencies. So it's nice to have tools to actually share these kinds of recordings. The nice thing is that you can, because the SIGMF data is just like a plain sample file, you can just do memmaps into your sample array and index them like that. So at DeepSig, we applied machine learning and deep learning to sort of RF signal processing in general. So we wind up recording a lot of radio captures, and we use SIGMF internally to keep track of what we recorded. And then there's this GRCon paper where we discuss some usage patterns that are kind of useful. So my goal with libsigmf was to create static types. So we have these schemas that we've defined for JSON, but we're going to be using this in C++. It drives me nuts. Like every JSON library in C++ uses strings as keys to index values. And that just drives me absolutely nuts, because it means you're reproducing strings everywhere. And it's pretty likely you're going to have a typo somewhere that won't get caught at compile time. But if you happen to have great test cases, otherwise, I don't know, good luck. So SIGMF also supports this idea of namespaces. So there's the core one, there's an antenna one that describes what antenna you would use. You can sort of define any namespace you want. So you have like a point people to your description of that, and they can now get a sort of compliant, like they will always be able to read and make sense of the metadata that you give them. So I wanted to be able to support any namespace that someone might make, and also still generate compile errors instead of runtime errors on misusage. So it's header only. So it currently requires C++ 14, although there's really only, we could lower that to 11 if there's a reason to. Yeah, and then there's CMake helpers, so it's a C++ project. We use CMake as a build system and make it easy to, when someone creates a new namespace, just make it easy to actually use that. Squash flat buffers and modern JSON together. So flat buffers, it's just another sort of like class generator. It's kind of like protobuf, but it's laid out differently in memory, and it has some other nice features to it. One of the nice things is that it has these sort of object description types, so you can sort of actually get this type that describes the object that you've generated from the schema, and that's what I use to take advantage of, or I use that to sort of parse through the structure and make sense of the object that has been created from the schema. Oops. Modern JSON is just used for the JSON serialization and deserialization, because why recreate that when someone else has already done it in a header-only format? And so I've seen people use sigmf in C++ using modern JSON before, but they just leave it as modern JSON, so they wind up copying their strings all over the place. So anyway, libsigmf uses both of these. Those are really the only two dependencies, and they're also both header-only. And we've releasing this under Apache License 2.0. So here's kind of how it works. There's this one class, the variadic data class. That is where most of the work is done. So you describe this flatbuffer schema, so sigmf core.flatbuffer file. If you have flatc already compiled, then you don't actually, like, it's literally just headers. If not, then you can include this in your, as a like submodule in Git, and we'll just build flat buffers for you. And then you get these class definitions for sigmf objects. So the flatc generator, the options we give it generates just the actual object that has all the fields exposed, so you don't have to go through like generator types. And then this is just a variadic. This actually shouldn't be a capital T over here, but ignore that. It's not actual C++. So there's this variadic template, and then you can access specific objects inside there. So the nice thing is that this actually works with any type of, if you can take any kind, it doesn't have to be sigmf in here. This could be any kind of just data storage class that you want. And then you can shove that into this template parameter and just squash together all kinds of different flat buffer objects into one convenient holder. So the way this works in practice is you create this variadic data class and say, I want a capture type. So this capture T is what's output from flat buffers or flatc. So once you do that, you have this new object that is parameter, and you can access all of the parameters inside that template using this access method. And so you get code completion in nice IDEs and editors. And of course, since you get code completion, that also generates compile errors if you use the wrong type or something. Down here, you can also, it returns a reference. So you can also just save that reference, and then you don't have to call the access all the time. So then you just say ref comment equals, this is my comment, and sample count is this. So it really couldn't be a whole lot simpler than this kind of usage pattern right here, except I made it a little bit simpler. So here you see that there's this access method. Down here I'm using this get method. So you'll notice that up here I create this annotation object. And then when I access it, I have to say, oh, by the way, I want the annotation object back out. And really, this is to say, like, I want the core namespace annotation object as opposed to some other namespace object. So like down here, there's the antenna one that's used. So what the get method does is says, I already know that this is an annotation. So this description T is a description for the namespace. So the core namespace is used here, and then the antenna namespace is used down here. Since it already knows that this is an annotation, it's just going to attach the annotation field of the namespace description. So what does that look like in practice? So like this is one of the implementations. We basically just kind of abused templates here, and we just attached the annotation, which is highlighted here, onto the get method, and then call the access method, but with the annotation type. And for the capture, we do the same thing. For global, we do the same thing. So that turns this code into this code. So it's a little bit nicer. To make a sigmf record, which is a whole description that has a global field, a capture field, and an annotations field, you just create this sigmf object type and tell it what kind of globals you want, what kind of captures you want, and what kind of annotations you want. So this would have a global with core namespace, antenna namespace. There actually is no antenna namespace for captures. And then the annotations would have core and antenna namespaces. So this gives you a nice type. And to go round trip from JSON back, here's a string that is describing some JSON file. Whoops. And we just call JSON parse, which comes from modern JSON. And object equal to that. And now you have your static object filled in with all of your sigmf metadata. If you want to go back, all you have to do is say make a JSON object out of this capture object, and now you're back as a string. So the round trip serialization is pretty simple, and you get all the benefits of a static type. So the code's available here. It's on GitHub, DeepSig, libsigmf. It's Apache 2.0. Yeah. So what can you do with SIGMF? So at DeepSig, one of the things we do is we do spectrum annotations. So winds up looking kind of like this. Just draw boxes around signals and label what they are. If you go a layer above that, then kinds of anomaly detections where you can drive through Arlington in Virginia and just keep note of what downlinks you see, and then draw heat maps over them with GPS coordinates. You can also do this sort of center frequency bandwidth kind of analysis where you plot a heat map of center frequency and bandwidths. So if you watch this and expect it, then it's a new signal. And then there's the breakthrough listen stuff. They're also doing similar kinds of things. And so with this, you basically just put in the annotations section of SIGMF, you say whatever you want about the signal. And then there are some core namespace features that you would fill in. And then there's also a handful of maybe specific things you want. Like there's no SNR one, so we have a DeepSig SNR namespace. But yeah, you just fill in annotations in the JSON fields. So Steve Croft is the lead at the UC Berkeley. They are working on finding aliens. So here's, I guess 30 years ago, it wasn't known that there were planets outside of our solar system. And so that's a relatively new idea. And it turns out that there's a lot of planets that could potentially support life, and they're just not very nearby. So here, this animation should show, yeah, this is, keep track of the year here. So this is over several years watching the reflection of various planets as they rotate around their sun. So this is one way of observing that planets are outside of our solar system, because you have the sun in the middle, of course, and then these planets they have a very long orbit relative to Earth, but you can see them moving, and that's just reflections of their sun that we're observing. And so this is made up of real images from the Keck telescope, and shows 7 years. So I think that their orbits are between 40 and 400 years, which is pretty long. But and then there's the TRAPPIST-1 system. This has apparently become pretty popular with kind of the SETI research people. It's kind of an appropriate name because it's the TRAPPIST system, and it's discovered by Belgians. So it's great to talk about it here. The reason it's interesting is because they have 7 planets, perhaps more, that are just very similar to Earth. So there's lots of potential there. And this is just an illustration, of course. So then the question is, if there's so many stars out there, many of those stars have planets that could support life. Where is everyone? There's the Drake equation. I don't know if anyone's familiar with that, but it is an attempt to say, like, let's enumerate all of the variables of, like, what the probabilities of things occurring that would cause life to exist. Given those probabilities, how many planets are there that might have intelligent life? And I think the first estimate of when they came up with the Drake equation, or when Frank Drake came up with the estimate, He decided in our solar system there were about 10, based on some probabilities. And then there's the Fermi paradox of if life is common, then why haven't we found it? So there's two ways. One is biosignatures. So this is, you take planets, and here's Earth. So just look for similar composition to Earth. And then there's Venus, and just look for biosignatures because it can support life. Then there's technosignatures, which is basically looking for signs of technology. So pretty much the SETI people only find signs of technology coming from Earth. So what you do there is you basically just collect signals and then look for structures. You can do this with really cheap SDRs. So the Newelec type thing is really cheap. The Pluto is also very cheap. All you have to do is ask a question and you get it for free. And then you just need a dipole. So yeah, so far only technosignatures have been discovered on Earth. So a little disappointing. And it's kind of like searching through a haystack, or a needle in the haystack. So the breakthrough mission was announced in 2015. So the breakthrough initiatives, I guess, and it was a $100 million mission to find signs of extraterrestrial intelligence. So the Berkeley group has 20% of the time on the Green Bank telescope, which is the largest dish on Earth, I think. Fully steerable. All right. And it's in the radio quiet zone in West Virginia. So they get 20% of the time on that, which is pretty substantial. So they have some infrastructure to support that, and it's mostly tons and tons of storage and high-speed digitizers. And so they collect, what this winds up doing is that they collect tons and tons of data. And then they have to process that for some kind of sign of signals that you wouldn't expect to see. So how do you do that? Well, they have this approach where they collect. This is relatively wide, or sorry, relatively narrow compared to their digitizer capability. They can do 6 gigahertz of bandwidth. This is only what, 30, 40. So they channelize this into smaller chunks. So the black lines that you see are just residuals from the way that they channelize things. And then they do some differential analysis. So there's lots of interferers that they have to deal with. So the Green Bank telescope is in quiet zone. Even in the quiet zone, you wind up hearing lots of things that you shouldn't. I mean, part of the problem is probably that I-81 goes through, major interstate goes through there, so it seems like there's lots of problems there. And then you also have satellites that are going overhead, and they don't necessarily respect the quiet zone when they're doing their downlinks. So the sensitivity of the Green Bank telescope is, because it is so big, it detects a lot of things that it shouldn't. And so this is looking at an example of their analysis. So they look at, here's 6 spectrograms that it's the same channelized data. They look at a star and then look just offset to the star, and then look back at the star, then look offset to the star, look back at the star, and then look offset to the star. And then doing that, they're looking for signals that basically just don't move. So if you're looking at the same star, you should see, if any signal that you see coming from that star or from that object should be there in all of these, and it should not be there in all of the off ones. And they also say that the geosynchronous satellites will also not appear in like they'll have some relative star. So any signal that you see in here but not here is really what you're looking for. So they have 3 different outputs. There's basically just time frequency trade-offs here, and a lot of it is in this sort of guppy, I think it's the Green Bank something pulsar data format, and some of it's HDF5 and these filter bank spectrograms, which are these things. So my claim is that this kind of highlights why. So in doing some background research on this guppy format is Green Bank specific. It's based on some other format, and then a lot of users of Green Bank have a slightly modified format of this guppy data. So it seems like SIGMF may be useful to the radio astronomy community, but we'll see if it's widely adopted or not. So here's they're trying to point out some signals that they see in the off and not off. So one approach that they're interested in is rather than doing this kind of differential analysis where, because you have a time delay here, right? So that your signals may have moved in time, or you don't capture, you capture some signal that it's just intermittent. So that wouldn't show up in all 6 spectrograms, even if it's there in all of them. And that's why you have to do 3 passes to say, like, is that signal really still there? But you're still losing these bursts, and the bursts are kind of the interesting things. So they're interested in kind of a machine learning approach to detect all known signals on Earth as well. So one of the ways to test that their algorithms are working is to look at the farthest known thing that is emitting that they can definitely detect and know what it is. And so that's Voyager 1. So that's kind of the sanity check on a lot of their algorithms. So here you have the Voyager 1 spectrum, and it's 12 billion miles from Earth, so pretty far. If you can detect that, then maybe you have a chance at detecting other things. So here's kind of the zoomed out version. It's not a very strong signal. And so you zoom in on it and you start to see that, okay, there's a carrier and there's the sidebands that have data on them. Zoom in further and you can see the actual signal characteristics. So they have this tutorial on GitHub that you can follow along, and it's a Python notebook that shows you you can actually detect, like they give you the data set for their Voyager capture, and then you can do this zoom in and see Voyager. And so here's what that looks like. They have, again, like it uses this filter bank file, but there will be SIGMF captures at the end as well. So this is another URL to the same material, I think. Yeah, so then there's also these fast radio bursts, which are interesting, and these are on the order of milliseconds. So these wouldn't necessarily show up when you do the 3 scans to the on, off, on, off, on, off. Because they're so short, using a machine learning approach to do this is useful, and SIGMF basically allows you to easily say, like, here, like in this time, in this frequency, here's this burst, this fast radio burst. We're going to build up a machine learning data set to do with these fast radio bursts and do our learning on that. There's only 2 of these that are known to repeat. So yeah, so that's the fast bursts. So the Berkeley study group has actually created a data set. They've synthetically generated some of these and then trained some neural networks to detect is there a fast radio burst here or not. And using a CNN, they worked through 100,000 simulated bursts. And they were able to find 72 bursts that their traditional algorithms did not. So it seems to be a useful approach. And these are just more of the bursts. And then there's paper links in here as well. The author that did that was Gary Zhang. He's at Berkeley. And then, yeah, like I mentioned, the approach that they're taking is they would like to identify, if you can identify all of the Earth signals first, then just remove those, look at what's left, then you have much fewer candidates to look through for finding ET-type signals. And then there's another paper going through some anomaly detections. So that's all. So if you want to go for the Berkeley data sets, they have a blog post here, and then actual data you can download here. And then they also have those Voyager tutorials where you can download their Voyager data set and walk through demodulating the Voyager signal. And then libsigmf is available on GitHub. And we also have a sigmf recorder, which uses UHD and just dumps out sigmf data sets. We'll be supporting some other radios as time allows to develop. So that's all. Any questions about libsigmf? Maybe some astronomy, but I'll probably just have to punt to the SETI people, and they're also on social media. So, yep.
Is there any particular reason for having two separate files for data and metadata in sigmf for one?
Yeah, so the question is why use two different files, one for the metadata, one for the sample data. The reason is a lot of tools, at least like my personal opinion is that a lot of tools are easier to write and less fragile if you keep your samples completely in their own, like you either have to have a fixed size struct in somewhere in your data, and then you can mem map. So like personally, I really love mem mapping samples because I don't have to load the whole thing from disk all at once. And if I need to do that, then I just explicitly load them. So to do a mem map, you either need a fixed size struct or you need to read the struct to figure out how much data to skip to get to your samples. The other is one of our convenient usage patterns, at least that I've discovered, is using a really big disk to actually do your storage, and then maybe like do symlinks to like a read-only partition so that people can't mess it up. Yeah, so you can do nice tricks like that. So like you don't have to necessarily have your metadata and your signal data in the same spot. With it. Otherwise, you have to develop very, very specific decoders to read a sample file.
Doesn't the sigmf spec have like something on the archive?
Yeah, the sigmf spec allows you to squash them together into a tar archive. But I guess you could do that even without the spec. It's just the sigmf spec allows you to call it a .sigmf file.
Right.
I think like in the sigmf repo, there should also be like all the rationale, the explanation of why this was done.
Yeah, that's true. We should. Yeah.
If you want more detail, you can probably do that. All the
Looks like it is only for radio signals. Can it also be used for optical astronomy? Because comparing optical with radio can also help a lot. And you can use the same kind of.
Is this in the search for ET signals or in? Oh yeah. So I think one of the reasons that they don't use optical searches is they're looking at planets that are much further out than you can typically see with optical, like just images. That's a radio astronomy thing that I'll have to punt on. They did mention in this slide with the animation.
More wondering about your metadata.
Oh.
Can it also be used for optical?
Oh, I see.
To compare optical to radio sources.
Yeah, there's nothing. There's not really anything particularly specific to radio. It's just a JSON field with some keys, right? So you would define keys that you want to share image data with, and then release that as a namespace and share it with whoever you wanted.
Can you share your experience about using all those machine learning frameworks and libraries with complex signals where a lot of information is contained in the phase and you can't really split it up between in-phase and quadrature?
Yeah, so that question was on deep learning frameworks and complex sample types. It's pretty weak. I know that TensorFlow has complex data types. None of the neural network operations actually work on them. There are like TensorFlow ops that work with complex data types, but none of the actual neural network layers do. There's some technical challenges there. And there's also been papers, I think Joshua Bengio's group put out a paper comparing complex neural networks to equivalent non-complex neural networks. I think the results basically showed that it wasn't particularly useful. So maybe it doesn't matter. I also know that PyTorch or libtorch or Caffe, whatever you want to call it these days, they just don't even have support for any complex type, I think. I guess. Doesn't work. All right.
Why did you use the 2.4 gigahertz for listening? It's embed and now it's very.
Yeah, so that's a SETI-specific question. I suspect that they were using 2.4 gigahertz in this example just to show easy interferers that they were. It's showing the procedure that they use to remove interferers, and that's probably just where they're guaranteed to get interferers. I doubt they're actually searching at 2.4 gig.
It's also the hydrogen line.
Oh, okay.
Comet spin.
He knows more about this than I do.
It's used.
All right, I see.
We use the microwave on the same frequency because it spins in the air.
Makes sense.
Microwave 2.4 and the hydrogen line is 1.4 something.
For the video, there was just discussions on which elements resonate at which frequencies.
Is there any type of labeling tool that I can just go visually to my recording and then click and say, I want this to be this metadata?
Yeah, it's a great question on is there any like automated labeling tool? I don't think that there is. I think there's a GR SIGMF which has just uses modern JSON. I don't know that it's attached. I know that they have said publicly that they have a fork of InSpectrum that I think that they use with SIGMF. I don't know if I don't know why not, but yeah, I think no.
So is that for private?
Yeah. About releasing it. I don't know why.
I'd be interested in getting.
Yeah, I think if someone actually released one, maybe later today, some people can just hack together SIGMF into InSpectrum and then contribute that back. Yep. Yeah, so other groups using SIGMF. My understanding is that there are several independent groups using it. It is just a GNU Radio spec, so like it's part of the GNU Radio Foundation, like one of their projects. So it's not specific to my company at all. It's just we're releasing a library to use it conveniently. Yeah, I personally am not. I believe that there are several. I mean, there's several companies using it for sure. I know that in the U.S., several government agencies that do research, like the NRAO, is using it. I think what's the one in Boulder? They do the timekeeping. NIST, yeah, I believe NIST is using it. But yeah, I don't have a public list. I don't know if there is a public list of claimed users.
You should ask your manager.
Yeah, I'll ask my boss.
Yeah.
He loves SIGMF.
Who asked the question? We can already get them.
Oh yeah, I've been shotgunning questions.
We're actually running out of these.